Okay, so last time we ended up with the vectors. We were adding vectors. We added three-dimensional no, we were multiplying vectors. So we did the dot product was the last thing we did, right? And quick review on dot product, also called the scalar product, also called projection of a vector. It is a commutative multiplication, so that you can reverse it and it's the same answer. It's also distributive, which is nice because these rules are kind of rules that we're used to dealing with multiplication. And the multiplication goes like this: if you have two vectors A and B, and you are using the scalar product or computing the scalar product between them, you take the x components of each and multiply them together, and the y components of each and multiply them together. Here it is. And the z components of each and multiply them together, and then and those are just the magnitudes of those components, actually, just the coefficients. And then you add those three products together to get the overall scalar product or dot product. Right? And from the definition of the dot product, we can actually extract this one little nugget where we can calculate the angle between two vectors. If we know two vectors, and we can calculate their dot product by using this particular formula, and then divide by the product of their magnitudes, then we can get, that will equal the cosine of the angle between the two vectors. So we just take the inverse cosine of that little thing and we get the angle. So two big things come out of that dot product section. First, how to calculate the dot product. Second, how to calculate the angle between two vectors. The third thing, of course, is kind of implicit in the dot product thing, and that is what the dot product actually does. It projects a vector onto another vector so that you can know how much of a vector is pointing in the direction of another vector. And that kind of comes from looking at like a picture like this and saying how much of B is pointing in the direction of A, and you can project B onto A, and you can also project A onto B's direction as well. Same value in the end. So, here they do an example of how we use the dot product later on in this class. You have a force pulling on an object. It causes the displacement d. So these are two forces, or sorry, two vectors. And the work of two vector, the work is equal to the force dot with the distance. So F dot d, in other words. And so we do the dot product there, and we find out that the work ends up being negative 98.7 newtons centimeters in this case. We multiply the x components together, y components together, and z components together. And you notice here that only the y components actually have a value that comes out. This one has a 0 value for the x component of the displacement. This one has a 0 value for the x component of the force, for the z component of the force rather. So the first and third terms actually just disappear, and it's only the second term that contributes. And why is that? Well, it's because, of course, the displacement had J and K components. The force had I and J hat components. So the only thing that they had in common was the J hat components, or the Y components, right? Those are the only things that the only direction that they shared. So that is the dot product slash scalar product slash projection of a vector product kind of thing. Now here is the more complex of the two, the cross product. And we also use the cross product in physics. It is used more in things that involve rotational mechanics, which we will get to later this semester. But the cross product is denoted with the cross in between them, so hence the two types of multiplication signs that we use in arithmetic these days. In computer language, we usually use the dot for the dot product, which, if you have two scalars, the dot product of two scalars is actually just multiplication, it turns out. And then you use the x for the cross product. And then you use the star for the multiplication, for just scalar multiplication. But anyway, this is the cross product, and the cross product is a true vector multiplication. This is often called the vector product because it gives you a vector as an answer. So there's a direction that comes out. Whenever you have a cross product of two vectors, the answer that comes out will always be 90 degrees to both of the vectors being crossed. So whatever vectors you start with, A and B, if your answer is C, the vector C, C will be perpendicular to both A and B. You say, how can a vector be perpendicular to two other vectors? Well, any two vectors, whatever direction they're pointing, if you bring them together, will define a plane in space somewhere, because it's like two crossing lines, right? And your vector will be perpendicular to that plane, either going into the plane or out of the plane. That's essentially how it works. Now, how do you figure out if it's going into the plane or out of the plane? You get your first introduction to the right-hand rule. Those who have taken physics before have heard of this. But in the right-hand rule, we use this is just a. There's no magic to this right-hand rule. It's just a rule that somebody made up to help us remember which way it goes. You could make the left-hand rule if you wanted to, or whatever, or some other kind of rule. But this one is what most people use. And the right-hand rule for cross products say that you point your fingers in the direction of the first vector. So in this case, A, on this problem, whatever direction A is pointing. So let's say that A is pointing over here towards Packard. So I'm going to point my hand towards Packard. And let's say that the vector B is pointing towards the telescope. And what I do is I turn my fingers now, turn my hand toward that vector. Okay? So pointing my hand this way, I turn my fingers this way, because that's the way the other vector is pointing. And my thumb will always point in the direction of the third vector of the answer. Okay? Now, if Packard is my first vector and then my second vector is pointing downward towards the board, then I would have to actually rotate my hand until I could point my fingers downward towards the board. And then my vector would be this way. What if it's the first one is Packard and the second one is pointing towards that yellow cord retractor up there? I'd have to rotate my hand upward until I could point my hand that way, and it would be off in this direction. Now that's just kind of a general tool for figuring out the basic direction, off in that direction somewhere. The mathematics will give you the exact direction, but that just gives you an idea of what's happening. Because in physics, we often want to have an idea of what's happening, right? It's a matter of estimation or just figuring out what's going on in a problem, whatever. So we often want that. So the right-hand rule becomes quite important. Incidentally, I hat dot j hat gives you what? Can you guess? So x and y and z, right? I, j, k, I hat, j hat, k hat. If our x is this direction and our y is this direction, I put my hand in the direction of I, cross it with j, and what's pointing up? K. So I hat crossed with j hat equals k hat. And that is true for, we usually call that a right-hand coordinate system because it obeys this right-hand rule for the cross product. And we like to work in right-hand coordinate systems. And again, there's no real magic to a right-hand coordinate system. There's no real physical reason, except that if everybody uses right-hand coordinate system, and I say I'm in a three-dimensional, rectangular coordinate system, and this way is x and this way is y, you know which direction z is supposed to be. If this direction is x and this direction is y, then I, j, k is down. So all you need to know is two dimensions, and you know where the third dimension is. Everybody in the whole world is, because everybody in the whole world uses a right-hand coordinate system. Okay? So it's just a way of making sure that everybody is on the same page. Now, of course, there will be people that will buck against the trends, but we curse them and move on. But anyway, okay. So, cross products. So we're going to have to do the cross product in two steps, essentially. at first, because we've already learned how to do the direction. Now we need to know what's the magnitude of a cross product, what's the actual value of the vector for its component, for its magnitude. And that's what this is. The absolute value, or this is also the magnitude of, right? When you put an absolute value around a vector, it means the magnitude or the length of the vector. So the length of the vector A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Now this looks very, very similar to the dot product, right? What did the dot product say? Dot product was the magnitude of the first times the magnitude of the second times the cosine of the angle between them. This one's the sine of the angle between them, so it's different. Remember, with the dot product, if you had two vectors that were not collinear or not antilinear to each other, in other words, they weren't, if you had two vectors that were orthogonal to each other, or 90 degrees to each other, you got that cosine of theta, which was cosine of 90, which is 0. So any two vectors that were 90 degrees to each other, the dot product ended up being 0. Here, it's not that at all. Here, it's the exact opposite. Any two vectors that are pointing in the same direction will give you a cross product of 0, right? But that makes sense, doesn't it? Because can you do the right-hand rule with two vectors pointing in the same direction? Can't, right? It just can't be done. So that kind of makes sense a little bit. So this one, the vectors have to be pointing in different directions in order for this to work. Yes.
So okay, so I solved the cross product. What's the answer? What's that?
Okay, so that we're getting there.
Oh.
I'll get to it.
Or
So
even the dot product.
What's that?
The dot product just tells you the magnitude.
What the dot product does is it's a different product than the cross product. It gives you different information about those two vectors. Okay? It tells you how much of one of those vectors is pointing in the direction of the other vector. And essentially what it does is it tells you how much of those vectors are pointing in the same direction, and then multiplies them together. That's really what it does. Okay? The cross product is going to do something quite different. And the cross product is more the cross product creates what we call a pseudo vector physically. So these two vectors might represent physical things like force and distance, or displacement, or something like that. But the vector that comes out as the answer of the cross product is not a real physical vector. It's just a representation, what we call a pseudo vector. It's a representation of what these two vectors can do together. You can think of it as. So it's a little confusing. It is a construction. It's a construct of the human imagination, but it's a useful one. Now, of course, mathematicians will completely argue that and say, well, it's all theory anyway, and this vector is just as viable as the other vectors, but we're talking physics here. In physics, a vector either means something or it doesn't, right? And vectors, we want them to mean something. So if it doesn't really mean something physically, then we have to understand what it means kind of existentially, maybe. I don't know. But these vectors that we create here, these pseudo-vectors, do have meaning, but they don't have a direct correlation to something in the real world, necessarily. I mean, to say that is oversimplifying, but I'll show you what I mean in a minute. It'll become obvious soon. Anyway, so this gives us the magnitude or the length of the vector that we're trying to get, the answer, in other words. It gives us the magnitude of the answer, but the direction, we have to use the right-hand rule or something else to figure it out. So let's a couple of the rules of cross products. One of them is quite interesting, is that it's not commutative. It's anti-commutative. If you switch the order around, it actually puts a negative sign on the answer. So if your answer to A cross B is this vector right here, then your answer to B cross A is this vector this way, right? In the exact opposite direction. So that's kind of strange. Here they talk about the right-hand rule, which I don't like their version of the right-hand rule, but you can look at it if you want. So here is an example of where the cross product is used and what it is used for. The torque that is caused by a force acting at some distance, some displacement. So this displacement or this distance vector is the r vector, The force that we're going to apply is the F vector, and this is the example. We have a wrench that's applying a force on this nut here. We have this distance between the center of the nut out to where our hand is on the wrench, so that's the R vector. It points from here to here, and our force vector acts at the end of that, off in this direction, this angle phi here, right? And to get the torque that is applied, we use R cross F. We use the cross product for this. Now, I just got to finish telling you that these things are pseudo vectors. The answer to a cross product is a pseudo vector and doesn't correspond to a real physical thing, and that's true. Torques are not actually true vectors, they're pseudo vectors, and it's not really a real thing. It's a construct that we created to help us to do the math and to understand multiple forces acting off axis from each other. Because it's really just a force. It just happens to make the thing twist, right? And that's just more complicated than we wanted to get in our mathematics. So to account for that, instead of making the mathematics complex, we made the physics a little more complex. Because naming things and calling things, giving names to things is easier than giving mathematics to things. Right? So anyway, the point is, we constructed this thing called the torque, which combines the idea of a force and a distance from some kind of center of rotation for that force. And this torque is now the answer to this cross product R cross F and is a vector. But why does it not represent something in the real world? Well, use the right-hand rule. R cross F, that means the torque is pointing out of the page. In this situation, is there any thing in this physical situation that's pointing out of the page? Is there a force pointing out of the page? There's nothing pointing out of the page. The only thing that you could think of is if you took a line and drove it right through the center axis, the turning axis of the nut, there is that axis pointing out of the page. That's it. Right? And so you think, well, why is this important? Well, it's important to have the math represent something physically, right? So that's what it comes down to. It's kind of interesting, though. When you have if you used a screwdriver to do the same thing, your torque would still point out of the page in this situation. If you used a screwdriver and the screwdriver had a little nut driver on the end of it, and you were turning the nut that way, your force would be sideways again, and the distance would be much shorter because it would be between the center of the screwdriver and the outside of the handle of the screwdriver, essentially, but down the long axis of the screwdriver. So it would be the same direction. And you think, well, how am I going to get more torque on the screwdriver? Because on the wrench, what do you do to get more torque? You make that arm, that R, longer. You put a pipe on it or something, right? And that makes your torque longer or bigger so that you can turn around. Well, how do you make the torque bigger on a screwdriver? You'd have to make the handle fatter. And have you ever seen a screwdriver with a handle like this? Every once in a while you see a screwdriver that has a hole in the top that you can stick a bar through and twist, and you can use them that way. But not often. That's kind of an old thing. So you don't see those very much anymore. It turns out that if you make the handle longer in the direction that the torque is pointing, you can actually get more torque, which is weird. So while the torque is a construct, there is something there, right? And I don't know the exact. I'm sure there are some engineers that have studied this and done some research on this, but it's certainly true. If you want to pull out a screw, one good way to do it is to get a longer screwdriver. It's a screw is struck. It has limitations. It's not exactly linear, but a small screwdriver is harder to pull screws out with than a longer screwdriver for some reason. So maybe there's some knowledge to be had there, some things to learn there. I don't know. So anyway, the angle between the vectors does matter, and we can calculate the magnitude of the torque by you take the length of R and the length of F times the sine of the angle between them. This gives us 3.21 Newton meters here for that torque. For for a different, if you apply it at a different angle, so this one they do a 40-degree angle and a 45-degree angle, whatever. So at a different angle to give you a different torque, right? Your maximum torque, of course, will happen when? When does your maximum torque happen in this equation? R doesn't change. If R doesn't change and force doesn't change, maximum torque is going to happen at 90 degrees now, right? Before, the maximum dot product happened at 0 or 180. Here it's at 90 or 270 or whatever. So and in this case, we can actually figure out if we put these two things in the xy plane. So if x is pointing this way and y is pointing this way, these two vectors are in the xy plane, and our torque would be in the z plane, or in the z direction. So that'd be the k hat direction. That's how they determine the direction here, is just by using the right-hand rule. But that's not the only way you can do that. Also, the distributive property is in effect here. If you have A cross B plus C, then it is A cross B plus A cross C, so the distributive property is in effect. Remember that our the commutative property is not commutative anymore, it's anti-commutative. And notice, like we said before, if your vectors are pointing in the same direction, they equal 0 when you take their cross product. I hat cross I hat is 0. J hat cross J hat, K hat cross K hat, they're all 0. However, I cross J is K. We already said that. J cross K is I. K cross I is J. J cross I, the opposite of this is what? What is J cross I? Negative K hat, right? K cross J is negative I hat, and I cross K is negative J hat. So if you switch these around in order, all these become negative. And here they talk about that right-hand rule, or that those right-hand systems that I talked about, where we choose a right-hand system. Now, here is the doozy. Let's do the cross product all out in all detail. We already did this for the dot product. We did something just like this for the dot product, except with the dot product we had a bunch of stuff, all I hats and I hat cross, I hat and J hat cross, all those, not cross but dot, all the dot products became scalars, so we didn't end up with vectors. And we had a bunch of zeros just like we're going to have here. But this one's going to be a little bit different. Remember, the last one, everything on the diagonal went to numbers, became numbers, and everything else went to 0. And this one, it is just the opposite. Everything on the diagonal is 0, and everything else comes out with numbers. Right? So we have a lot more terms that come out. When you multiply the two x components together, you get 0 because I hat cross I hat is 0. But when you multiply the x component with the y component, you get a plus k hat thing. Right? So x, y, and the order matters here because this is A cross B, right? So A sub x, B sub y gives us a plus k hat. And when we do the A sub y, B sub x, just the opposite order, we get a negative k hat. So we get two k hat terms here. One's a positive k hat term, one's a negative k hat term. We have to combine them and see if we get some overall term. They might combine to be 0, but they might combine to be a positive number. They might be combined to be a negative number, but in any case, we have to combine them to see what we get for our k hat term. And in the end, we're going to have 3 terms. We're going to have an I hat term, which is going to come from this term and this term. We're going to have a k hat term, which is going to come from this term and this term. Then we're going to have a j hat term, which is going to come from this term and this term. In the end. So in the end, this is the formula. You take AYBZ minus AZBY and multiply by I hat. AZBX minus AXBZ and you multiply it by J hat. And then AXBY minus AYBX multiplied by K hat. Is it possible that one of these turns to 0? Yeah, it is possible. But, the more likely situation is that you get numbers out of here just because there's more possibilities for that to happen. So here's a more succinct form. The components, the scalar components of the cross product A cross B equals C. You're going to get C sub x. The component of the x component of C is going to be AY minus BZ, AY BZ minus AZ BY, and so on and so forth. So very, very succinct. And I would recommend that you have these written down somewhere. And speaking of which, I have something for you. If you want. I'm running out of these things.
I think I still have mine.
Yeah, I see you guys still have them. So this is a little physics cheat sheet. I got a bunch of these for free a long time ago. And this is going to be, I think next year will be my last year I'll be able to give them out. But these are, you can use these during your homework and your exams. And they have a lot of this information on them. So they have three-dimensional coordinate systems, two-dimensional coordinate system, vector algebra stuff, scalar product, cross product, right-hand rules, factor products, and all these things. So useful. Do you have any questions?
I don't think so.
Very useful, quick way to get information. While I don't allow notes or cheat sheets on exams, I do allow that, and I do allow your textbook. And you know, anything that you want to write in your textbook, you're welcome to write in your textbook and take with you to the exam. Even if you don't have a printed textbook, you can still make notes in your online textbook if you have it as a PDF. In your electronic textbook. Did you guys know how to make notes on a PDF? It's pretty simple. You have to open it in an Adobe Reader. Let's see if I can. Where's the textbook? Here it is. This is a different. I'm opening a different textbook in this. But if you want to make notes in a PDF, you open it in Adobe Reader, and you go to Sign, and it gives you the option to insert text, add text to it. And then you click on this. It'll give you a little text thing here, and then you can click anywhere you want and add text to your book, however you want. So you can make notes in here. And then once you've done that, you need to save it. Save it when you're done, and then it'll save that text next time you open the computer. So you can do that, or you can print it off and write in it. It's up to you. If it was me, I would just print off the key pages that have the formulas that I need and maybe some examples that I really need. But that's just me. Having the PDF is nice because you can search it, or online version as well. So here's another example of the cross product where we're going to actually use the component version of the cross product. When we use the component version of the cross product, it doesn't tell us the magnitude and the direction necessarily, but it gives us all of the information to calculate the magnitude and direction because it gives us the actual vector components, right? So a particle in a magnetic field, when it's moving through a magnetic field, it can experience a force if it's an electric particle or if it has a magnetic moment to it. But the forces that it feels will always be governed by the cross product. It will always be some kind of twisting motion or turning motion, always, which is both annoying to deal with, but it's also extremely useful. This is how we get charged particles to turn in circles. So if you want a particle to go around and around in a loop and get faster and faster and faster, the way you do it is you put it in a magnetic field. And that's how we make accelerated particles. And they use those in medicine. PET machines use those. We use them in science, accelerating particles to smash them into each other and see what they're made of, that kind of thing. But they're used in all kinds of things. So magnetic fields are extremely useful when we're dealing with charged particles. And even when we're dealing with non-charged particles. Because before they really understood how to do this, they were studying. It was actually Madame Curie's kids here were studying the neutron. They didn't know what they were studying, but they were studying some particle that had no charge, and it was about the size of a proton. And they were trying to control them because they're quite dangerous when they come flying out of a nuclear radioactive particle or radioactive substance. These neutrons can do damage, and they all died from it. But the point is that they eventually discovered that even though they're not charged, neutrons aren't charged, they do have magnetic properties, so that they can be controlled with a magnetic field. So. And that's one of the things we're trying to do now, is to control the neutron flux coming out of radioactive reactions, like fusion reactions, so that we can make energy out of, like, water. If we could make energy out of water, that would be really great, because we got a lot of water. Anyway, so in this case, the force on a charge in a magnetic field is equal to this constant. Now, this constant is called, I want to say this one is Xi. K-S-I, I think. I can't remember, but I think it's Xi. So we have this weird Greek letter Xi, and we're multiplying by u, and we're crossing that with b. So you can multiply any constant times a vector. We know that, of course. It's just a scalar times a vector. But then we have this cross product, u cross b. Right? And it turns out that you can multiply by the constant before you do the cross product or after you do the cross product. Doesn't matter. But if you do it before you do the cross product, you're only going to multiply it by one of the vectors, not both. This doesn't have a distributive law, unless there's parentheses around the u cross b. But even if there is parentheses across the u cross b, it doesn't make any difference. But anyway, the point is, this does not become mu xi. Cu and Cb, it's just Cu. So, anyway, here's our u vector. U vector is the velocity, actually, in this case. We often use u for velocity, unfortunately, because that's confusing. And then the b vector, so the magnetic field, is also a vector, and it's pointing off in space somewhere. So here's our magnetic field vector. And we want to do the cross product between them. So we go back to our cross product components. The x component is going to be AYBZ, or in this case, UYBZ minus UZBY, and that will give us the first component of our vector. And they're going to do that right here. And it turns out that the component of the answer, which is the force, this is called the Lorentz force, is 8.3 times Xi. And then they do it for the y, 3.2 times Xi and 19.4 times Xi. And once they have all three of those, you can calculate the magnitude of the overall vector. You just square each one of them, add them together, take the square root. Pythagorean theorem. Right? Kabang. And if you want to know the angle of this final vector, then you're going to need to know the magnitude of the magnetic field, 7.6, and then we use the dot product divided by the magnitudes, and then take the inverse cosine and get the angle between them. And it turns out the angle between them is 90 degrees. So here we're using the cross product to calculate the force vector. Then we use the force vector to calculate its magnitude. Then we calculate the magnitude of the magnetic field vector and use the dot product definition to calculate the angle between them. Now, it seems like a lot of work, and it is a lot of busy work. It's a lot of arithmetic, which is annoying. The beautiful thing is you only have to do this for 1 year. Your freshman year is the only time we'll make you do this kind of stuff, and after this, we'll teach you how to use MATLAB, and you'll make computers do it. So it's not that big a deal. If you're going into mechanical engineering or civil engineering, one of these mechanical fields, or like anything using mechanical, you will have to take statics, which is like crazy vector problems, all mechanical vector problems, and all this kind of stuff constantly, dot products, cross products, dot products, cross products. But we just let you use a computer to do it for the most part. So. Is anybody in here taking statics? I don't think so. I had 3 students in statics last year. It's pretty amazing. All right, so that takes us to the end of vector products, and that's a big deal for this chapter. It's pretty much the whole idea, the whole purpose of this chapter. So to get through that, and we're done with chapter 2. So, I can't remember if I finished the chapter 2 homework, but I think I did. Can't get it anyway, doesn't matter. So, I think there's something like 10 problems or 8 problems or something like that. Does anybody know how many problems are in chapter 2? 10 problems? Yeah. That's about right. So it should give you plenty of kind of exercises doing working with vectors. And the reason I don't give you too many is because we'll do plenty of this later. You'll get plenty of exercise with vectors. You just need an introduction to them. That's not bad. We should be done with chapter 3 by the end of this week. And that's where we want to be. Yeah, so laboratory will be, was it 10 or 9? I can't remember. 10 o'clock? Oh, right, 10 o'clock. So 10 o'clock lab on Thursday, and we'll be meeting with Tommaso, U3, Tommaso, U2 and Tommaso. And so we'll have good lab. And we'll, we have another student that's taking this class I mentioned, right? He'll probably just do his labs on Fridays, or I might send the lab stuff to his house so he can do it at home since he's working so much. All right. And this video